Imagine everything around you, your phone, the air, even light, is made up of tiny particles doing the weirdest things you could imagine. Things that can be in two places at once, things that can instantly talk to each other across space, things that don't even seem real until you look at them. That's quantum physics. It's like the universe has a secret set of rules it follows behind the scenes, and they're nothing like the rules we see every day. Crazy, right? So let's just briefly talk about quantum physics today. Quantum physics, also known as quantum mechanics, is the fundamental physical theory that describes the behavior of matter and of light. Its unusual characteristics typically occur at the scale of atoms and even below the scale of atoms. Okay, so now the question is, why is quantum physics even important? And what can we use quantum physics to do in our everyday life? 1. In electronics. In most electronics, transistors are the basic components, and transistors rely heavily on quantum mechanics. 2. In quantum computing. Quantum physics is used in allowing quantum computers to perform computations in ways different from classical computers. They also have the ability and the potential to solve what other classical computers cannot even solve, such as simulating complex molecules and factoring large numbers. Isn't that interesting? 3. In cryptography, quantum physics helps in encryption of messages, thereby ensuring that communication is ultra secure. That is why it is called cryptography. 4. In material science is the main importance of quantum physics because it seeks to understand the behavior of particles at the quantum level. As a result, it brings about the development of new materials with unique properties. In quantum mechanics, they are four basic concepts which one must understand and which I'm going to explain in seconds. 1. Wave-particle duality. Wave-particle duality is a concept in which stuff like protons and electrons exhibit particle or wave properties according to the experimental circumstances. For example, light can travel as a wave showing interference patterns, but in other cases, like the photoelectric effect, light acts like particles called photons. Part 2. The uncertainty principle, also known as Heisenberg's indeterminate principle. It is a fundamental principle in quantum mechanics that says you can't precisely know the position and momentum of a particle at the same time. The more accurately you know one, the less accurately you'll know the other. So if you try to pinpoint where a particle is, you'll mess up your knowledge of how fast it is moving or in what direction and vice versa. Knowledge 3. Superposition. Superposition is a fundamental principle in quantum physics which describes a state simultaneously until a measurement is made. It is essential in quantum computing because it allows the existence of qubits, which can represent 0 and 1 at the same time. Imagine a coin spinning in the air. It's both heads and tails at once, and once you catch it, it's either heads or tails. That's just the best way to explain it. 4. Entanglement. Quantum entanglement is a phenomenon whereby two particles become linked in such a way that the state of one instantly affects the state of another, no matter how far apart they are. Imagine you have a pair of magical dice. If you roll one and it shows a 6, the other one, even if it's on the other side of the universe, instantly shows the same result. It isn't total fiction. It's real, proven and used in stuff like teleportation and in quantum computing as well. Now, what are quantum systems? Well, quantum systems refer to any physical system which follows the principles of quantum mechanics. Here are the three quantum systems. Subatomic level. This is the basis of existence. And of course, we all know what this is. The subatomic level is made up of protons, which are the positively charged particles, electrons, which are the negatively charged particles, and neutrons, which are the neutrally charged particles. Together, this trio combination makes up the atom. 2. Quantum states. These describe everything about a particle, like its position, momentum, and energy. They are simply the mathematical descriptions of a quantum system. 3. Energy levels. Energy levels are discrete energy values a system can occupy. Think of it like the rungs of a ladder. Particles can jump between these levels by absorbing and releasing energy, but they can't be in between. In this case, they are known to be quantized. Scientists aren't just tinkering with particles for fun, well, some are. They're chasing world-altering goals. Here are three major things scientists hope to achieve in quantum physics. 1. Quantum computing. The goal is to build powerful quantum computers that vastly outperform today's best supercomputers. Why does it matter? Because it solves problems classical computers can't, like simulating molecules for drug discovery or cracking encryption. Boost AI, financial modeling, logistics, and climate simulations. It could revolutionize industries in seconds where classical computing takes years. Although we have basic quantum computers already, they're still noisy and error-prone. Scientists aim for a fault-tolerant quantum computer, the holy grail of computing. In quantum communication. The goal in this case is to create a quantum internet with unhackable communication using entangled particles. That'll be fun because messages would be impossible to intercept without detection. Goodbye, hackers. Quantum communication will enable ultra-secure banking, defense, and governmental communication. It could allow for new forms of information teleportation across large distances. Quantum key distribution, QKD, is already being tested via satellite and fiber optics. It's like giving your email a force field. Quantum gravity, the theory of everything. The goal right now is to combine quantum mechanics with general relativity into one master theory, a unified theory of physics. Right now, the rules of the very small quantum physics and the very large gravity spacetime don't get along. A unified theory could explain black holes, the Big Bang, dark matter, and maybe other universes. It's the ultimate mystery. How does the universe really work at every scale? Theoretical heavyweights like string theory and loop quantum gravity are on the case, but no experimental proof yet. Still very brain-exploding paper napkin doodle stage. So in short, quantum computers could change how we think, quantum communication could change how we talk, and quantum gravity could change how we understand reality itself. And that's why quantum physicists have the best combination of stress, ambition, and sleepless nights in science. A good reminder, just to be clear, quantum physics and quantum mechanics are literally the same thing, so don't get confused. Okay, so if you've made it this far in this video, please don't forget to like and subscribe to Nexus Physica for more content on astrophysics, quantum mechanics, and relativity. So, goodbye for now.